Hello, Professor. Today I'm going to introduce you to a gym equipment fault detection system based on IoT. The presentation will be divided into three parts. The first is problem identification, the second is system design, and the third is prototype implementation and front-end display. For problem identification, modern gyms face a key challenge. There's no efficient way to monitor the real-time status and health of exercise machines. Without timely maintenance, this can lead to equipment failure or even injuries. My project aims to solve this by using IoT and cloud technologies to collect and track vibration data and alert managers when issues arise. For system design, our system consists of three main parts. First, use a laptop to run pattern simulation equipment vibration data. Second, some AWS-based cloud services including IoT Core, Lambda, DynamoDB are responsible for data collection, processing, and storage. I also used AWS API Gateway and Lambda to receive front-end requests and execute business logic. Thirdly, the communication part uploads the equipment through MQTT, and the front-end accesses through HTTP interface. For the prototype implementation, I divided it into two parts. The first part demonstrates how the system collects, processes, and stores vibration data. For the second part, I will walk through the front-end interface and demonstrate its key features, while explaining how each function is implemented using Cognito, API Gateway, and Lambda. For the first part, first I created a thing in AWS IoT Core named Gym Management and obtained the device certificate and key. I configured IoT Core in the device side code. Then the device connects to MQTT broker through TLS handshake. After the authentication passes, it sends vibration data to the topic I set every 3 seconds. The topic is gym equipment data. The returned vibration data include device ID, the type of device, time step, and vibration. In order to process this data, I wrote a Lambda function named process equipment data. Host functions include parsing the received data into JSON format, and then extract device ID, vibration value, time step, and other fields, and convert the vibration data to decimal type to be compatible with DynamoDB, and then check whether key fields are missing to avoid reading incomplete data. Finally, the processed data is written into DynamoDB. I also created a rule in IoT Core named write data to DynamoDB to listen to this topic, gym equipment data, and then automatically trigger Lambda for data processing. For the second part, I will focus on 4 core functions: user login, real-time visualization, controls, and alert. I will first show the front-end interface and then briefly explain how it works. For user login, first enter the user login interface, enter the username and password, complete the login, and enter the main interface. In the aspect of implementation, I use Amazon Cognito User Pool to manage user identity and use implicit grant flow to complete it. The process overview is as follows. First, I created a user pool and an app client and add user. Then I configure the authentication mechanism for the relevant API, such as the getThreshold interface, and make it mandatory to log in before accessing. In the code, first configure Cognito user pool. When logging in, jump to Cognito hosted UI. After logging successfully, resolve the edit token from the URL and save token to local storage. Obtain the edit token of the current user, and the subsequent API request carries the token to verify the user's identity. For real-time visualization, you can see tables for different types of equipment, each displaying all devices in that category along with their current vibration data and current status. In the aspect of implementation, first I created an API called getVibrationData using API Gateway with cross-origin support configured to allow front-end access. Then I created a Lambda function named getLatestVibrationData. Its main tasks are handle cross-origin requests and curate the latest vibration data for all devices, and aggregate and return the results to the front end. This Lambda function is bound to the API gateway, so when the front end makes a request, the function is triggered automatically. On the front end, we use fetchData function to call the API, parse the return data, and assign it to all data value for display. To keep the data up to date, we use onMounted function and a timer to refresh the data periodically. For interactive control, at first is the default threshold. I configure the default threshold here. You can adjust the threshold for each device. For example, I adjust to 0.4, click Update, and the update will be displayed successfully. In the aspect of implementation, first, I created an API gateway interface with post method named Manage Thresholds. And configured cross-domain access. Then I created a Lambda function named Manage Vibration Thresholds, and its core functions include handle cross-domain request and parsing JSON data in front end request, extracting device type and a threshold, and update the threshold in the DynamoDB table, and return that processing result to the front end. And I bend Lambda function to API gateway to realize automatic trigger. On the front end, when the user clicks the update button, a post request is sent to the backend, and the modified threshold is submitted. If the update is successful, the system will save the new value and pop up a prompt box. The threshold updated successfully. If the update fails, an error prompt will pop up, and the value of the input box will be restored by the old value to avoid data inconsistency. For alert, you can see that when the current vibration value exceeds the threshold, the state will become exception. For the implementation, first I created a GET API interface named getThreshold and configured cross-DOM access. Then a Lambda function is written named getCurrentThreshold. The main process includes extract the device type from the query string and query the corresponding threshold from the vibration thresholds table in DynamoDB. If the result is found, the threshold value is returned, and if it's not found, the default value is returned. Finally, the function is bound to API gateway to realize request processing. In the front end, each line of equipment displays the current vibration value and status. The system will compare the vibration value with the threshold in real time. If it exceeds the threshold, it will be highlighted as exception to help administrators find problems in time. This is a request sent to the backend to get the current threshold.